Sometimes I care, sometimes I don't, depending on the application and other things. And even if the application has some kind of requirements for that, I can write the exception subroutines in such a way that I'm kind of solving the problem that I'm looking for. But still, the status of the processor might be polluted due to the out of order. Okay, now, we are very smart. We know how to deal with data dependencies. Now, we had structural hazards, which I said we need more resources. And in structural hazards, you know, guys, if you want to talk, you teach. It's very simple. If you have to communicate, feel free to take my place. You can talk to each other after the class. I really appreciate peer learning, which means that instead of coming and bugging me with questions, you bug your colleague. No, you know, I'm making a joke in a sense, but it's also true. When you talk with your colleagues, there are two issues. The one which is explaining, it's understanding better, and the one which is asking by the discussion might get a better explanation from somebody which it's on the same kind of universe. This is called peer learning and is very effective. I don't mind if you ask me questions, except if you ask me questions about the schedule and I'm telling you it's on the blackboard, right? Now, then one of the problems that we have, actually the last one, is what we do with control hazards. And there are many reasons why we like to deal with control hazards. Because somehow the control hazards do a lot of damage. In which sense? Tomasulo proposed a very smart algorithm, and I can, if I have instructions that I can scan in order, I can do wonders. I can fill all the reservation stations and execute, you know, like a train, going nice and clean. But unfortunately, in programs, I have branches. And each and every 3 to 6 to 5 instruction, I have a branch in RISC kind of code. Which means, if I'm not doing anything about those branches, Tomasulo will have to stop whenever a branch is coming, wait for the branch to be solved, and then continue. Now, this may or may not be fundamentally bad. If the reservation stations are kind of still full and the functional units can work, that kind of stall will not be visible. But if my functional units will die of starvation, because I have a lot of them, then the branch will actually kill the performance of the machine, which is coming to something which is not here, but it's a general kind of concept. When you define an architecture, and in general, when you make a circuit, an ASIC, a processor, whatever, you have to have good balance between resources. Then if you invest on one part only, and the rest are weak, and they feed that strong part, the system is as weak as the weakest link. This is true in reliability also, but also in that kind of processor which has to have a nice flow of instructions processed, and then I may have 100 adders, but if there are no instructions to feed them, maybe it's better to put 4. Now, because we have that kind of branches here and there, we like to predict them regardless of when we go scalar or superscalar, with dynamic scheduling or not. Because predicting a branch will let me execute further, continue the execution. And now there are two things here. A program, when you execute, it's like you A program in general, you can see it like a tree, where each node in the tree is a branch. Now, when you execute, depending on the data that you are crunching, you'll just produce an execution path in the tree. Then if you could create that path, or you can know it beforehand with 100% certainty, your program is actually a serial stream of instructions. But you cannot do that. Some of those branches are known at compile time because they depend on constants. They depend on things which are well known, statically known. But many of them are depending on data which you produce. And for that purpose, you have to do prediction. And when you do prediction, you have a number of possibilities. You do prediction and you start fetching in the direction that you predicted. Let's say this is the branch and I can go this way or this way. I say this, okay, and I will start fetching in this. And I will not execute anything before I know if I went in the right direction or not. Or I can also execute, which is I'm starting speculative execution. You know, I'm flipping a coin and I'm saying, here I do right. And not only that I'm, you know, taking a look on what I should do on the right, but I'm also going on the right. Anyway, even if you do speculative execution, you cannot commit what you did speculative. Because if you update the status of the processor based on speculation, you actually damage the information. Then if you execute in a speculative mode, you will store the speculative executed instruction results somewhere, and eventually when you know that your speculation was correct, you do the update. Now, there is no panacea universalis. Each kind of solution has pluses and minuses. Then if you go for speculative execution and you prove to be wrong, you have to return on the other side. Which means what? You dump calculation which you did, which means energy for nothing. And you also spend time in going in that direction, which you could spend in the other direction. And you will have to do a restoring, which is called, which will take also time and energy, because depending on how bad things are, you have to essentially flush the pipeline. But still, speculation, it's okay. We started with speculation on general purpose processors. Eventually, it came also in embedded systems. But most of the embedded system processors don't have speculation, you know, simple things. Because you care for energy and you don't want to spend energy in something which is like you send it maybe to the sink. Okay? Okay. Now, there are a couple of branch prediction schemes that we'll talk about. And we'll also talk about something which is a way to get rid of branches. Malicious or not, they are there, and without decision, we cannot live. Also in life, we have to make decisions, right? You made the decision to come to Delft. Was it a good decision or bad? Can you undo it? I became professor at the university. Can I say I want to become a medical doctor? No, why not? It's too late, right? I'm too old for that. I still can do it, but the cost will be very big. Okay, it's the same story here. If I make a decision and then I want to return, sometime too late, it will be a catastrophe. And that's the reason why it might be good to try to get rid of the branches. But it's not really that you get rid of them, you just hide them and you will see them. Now, let us look at the first prediction, the simple one. Then, if I have a branch, I can take the branch or I can go to the next instruction. Which means, what does it really mean? It means that if I take the branch, the program counter of the next instruction is the current program counter plus or minus a certain amount. Then I have to do an addition. This is not happening like, from heaven. I need to do that addition. And most processors do have a special adder for that. Modern processors. Simple processors, they use the normal ALU for that. If I'm not taking the branch, I'm doing program counter plus 1, which is I'm doing an increment. Most of you will believe that doing program counter plus 1 it's easier than program counter plus a constant. Plus 1, it's also a value. It's still an addition. In the worst case, it's as slow as any addition. Then you implement a counter, which is a simplified version of an adder, but still, in the worst case, you have to propagate the carry from the least significant bit to the most significant. But you can do an increment with less hardware. Now, that was we went around to other kind of field. Then a branch implies calculations. Now, I have to know whether I'm doing one or the other. In this case here, it's a 4-word instruction, then program counter is program counter plus 4. If one, next address is plus 1, you do plus 1, plus 4, plus 8, depending on how your memory is organized and things like that. Now, the idea will be to try to memorize somehow the previous behavior of the branch. Then, assuming that I have a branch, I would like to store somewhere the information about what I did with this branch in previous execution of this branch. Now, there are two fundamental issues here. First of all is how do I recognize a branch? A branch, an instruction in my program, has a unique address, which is 64 bits, or 32 bits or 16 bits. If I know that address, right, of that branch, I can associate to that address some kind of information about the previous evolution of the branch, taken, not taken. And I can make a long log of that. 1, 0, 1, taken, put 1, 0, put not taken, and I can make such a long log. That will give me exactly the possibility to recognize the branch and will give me exactly the previous evolution of the branch. I start with no history, but when I'm executing the branch, don't look there because there it's a simplified story. I'm just trying to explain you the concept. Then, while I'm going up, I build a history, and now based on the history, I may make a lot of beautiful tricks and try to find patterns. And let's say this branch that I'm looking at has a funny behavior. Each and every 10 executions is not taken, and the rest is taken. Now, that will be beautiful. However, that will cost me a lot of hardware. I have a lot of branches in my program. I cannot create such a huge table, even if I use a window of, let's say, 10 previous executions or 100 previous execution. It will mean that for each branch in my program, which I may have millions, I have to store the history of the branch. Then that's one, not possible. That would be my ideal to get that. Now, you know, in life, when you don't get the ideal, you go for compromises. And there are two compromises in here. First of all, I'm relying on the fact that, you know, programs are local. Then at a certain moment in time, I do not need to know the information about all the branches in my program. I will need to know about some branches in a certain range, because in here I'm moving. No, programs are mostly loops. And for that reason, instead of memorizing the address of all the branches in the program, I'm just saying, you know, I'm getting some bits from the address, not all of them, a couple of them, mostly in the least significant part of the address, and I use those bits as the identification for the branch, which means I get aliasing. Then more branches are contributing to the same history. That's bad, right? It is bad, and it is good. It's good because it's implementable. The one that I told you, we cannot make it. It's also good because I rely on the locality. There is little chance that branches will interfere with each other in loops, because I'm busy here and eventually I will move in another place, and branches which are aliasing each other will not be active in the same time. That's one story. And by that, I solved the dimension of the table. Then instead of, I don't know, 1 million entries, I will have 8 entries if I choose like 3 bits from the program counter to tell me something about the branch, like in here. And now I said branch history table. I can make a lot of beautiful things if I have a long history, but I can also use 1 bit. And I can say in that bit, a 0 if previous time the branch was not taken, a 1 if the previous time the branch was taken. And then I have a branch, then I am now fetching an instruction, I'm decoding it, it's a branch. What I do is some bits of the program counter will look in the table. And in the table now, if this is a branch, because I may have other instructions with the same bits, but I will not look in the table. If the instruction is a branch, I look in the table, I get an entry from the table, and if it is 0, I go for not taken. If it is 1, I go for taken. That's my prediction. Eventually, then I go for this prediction, but eventually I also solve the branch. When I solve the branch, I have to revisit the table. And I say, okay, the prediction was that should not be taken. And it was a 0 in the table. However, my practice demonstrates that it was a taken branch. Then I have to update the history. And what I'll do, I will toggle the bit from not taken to taken. Then, nice and clean, I'm collapsing branches, more branches in one entry, based on the fact that they will not alias due to locality. And I am using a simple history where I take the bit, I trust the bit, when I solve the branch, I update the bit. Right? And that should be, it's very cheap, no problems. It's not really working with the MIPS pipeline, but that's not the issue. Because in here there are some things, you know. Because in the MIPS pipeline, you know, I'm computing the target address in the same time as the branch condition. Then I don't need to do that. But in general, this will be the principle of doing branch prediction. Now, what we see is that this mechanism is beautiful, but if we are in the case of a loop, we do two mispredictions when we do a misprediction. Let's say I'm in the loop, you know, and I'm saying taken, 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 and then I'm at the end of the loop. Then it's not taken. And then I'm returning to the loop, where it has to be taken, but based on the not taken of before, I do again a misprediction, which gives me the idea that, you know, I was too strong on taking decisions. I should not flip my decision just based on a sample, you know. Also in life we do like that, you know. We have a friend, the friend is doing bad things to us once, we don't really decide to split. Twice, maybe not good. The same story in here, right? Then based on a certain reluctancy to change the decision, you may solve this problem nicely. You see, I'm at the end of the loop, I say not taken, but next time I have to take it. If I switch the decision, I'll be wrong, but I will not switch the decision. Then next time I will be good. And this is done with a predictor which has now 2 bits per entry in the history table. Then instead of having 1 or 0, I have now 2 bits. And I have 4 states. When I'm in 1, 1, this is a counter essentially, which you increase or you decrease. And you can make it on more than 2 bits. But 2 bits are essentially enough. Then when I'm on 1, 1, I'm sure I'm predicting okay. And if I keep on doing the right prediction, I stay there. If I make a mixed prediction, I'm not switching to 0, but I'm switching to 1, 0, which is, you know, I've been correct in the past, I made a mistake, but I still trust the past is the right one. And that will solve the problem that we just discussed. If the next prediction is wrong, then I will go to the strong non-predict. Then I've been wrong twice in a row, then it means that something changed. Yes?
So it's just like always taking it. In every loop, you always take it.
No.
Yeah, because in a loop, that's what will happen.
Sure, but at the end of the loop, you don't take it.
Yeah, so it's one mistake at the end of the loop.
Yes, it's one mistake, and if you will be returning, it's a nested loop structure. And
So
you
why not just do it always take? Like why all the hard?
because eventually you may exit the loop. You know, your program is also composed with other things. Then when you are in the loop, this will function okay. When you are exiting the loop, your prediction should adapt. Then in a loop, this mechanism of strongly taken, weakly taken will solve you the problem of nested loops to do 2 wrong predictions in a row. And when you exit the loop and you have other kind of branches, then this will help you to adapt to what's going on. Remember, this is a prediction. Prediction means it's not precise calculation. And what I'm trying to do, I'm trying to adapt my prediction to the evolution of the program. And this is a 4-state predictor. Then if I'm sure I'm right, if I'm sure I'm right on not taken, and I am weakly kind of things. The difference between the previous predictor and this predictor is that instead of using 1 bit per entry, you use 2 bits. And the update mechanism is slightly different, but not very much different. Now, in life, we also have other things but loops. And we have that kind of, you know, if then else structures. Now, there is something which is called branch correlation, which it's visible to you when you inspect the code, but it's not that visible to the processor when it's doing the execution. I mean, when you look at this code, you see that due to the nature of the code, there is a correlation between what branch 3 will do depending on branch 1 and 2. Now, this is a different kind of history. It's still history, but it's global history. Then what I'll do is I will look at the previous history of my branch, but I will also look at what branches which were executed before did. And then I make a prediction based on global information as well, to see where I am and what I'm doing. And I can now use 4 local predictors I forgot to say that here we just look at 2 previous branches, because I can look at 10 previous branches. But if I look at 2 previous branches, depending on how the previous branches were doing, my current branch will go taken or not taken. Now, because the previous branches can provide me 4 possibilities, I will have 4 predictors for each case. Then, depending on they were not taken, whatever. And this will result in this kind of structure. Then I have the same mechanism as before, with some bits in the address selecting the entry in the table. That's one story. And the update of the table will be done according to the procedure with weak, strong, whatever. But in the top of that, I'm using the outcome of 2 previous branches to make a selection between the predictor that I'm using. And I'm using a register, a sheet register, where I store the previous branch's outcome. Because I'm looking for 2, the window is of 2 branches. And then based on the fact that in here I have 0, 1, I will select the predictor in the middle. And this is making my prediction, being aware about my history as a branch and the history of the execution of the program. And in here, there are some performance data collected by the simulation of some spec benchmarks. And what we see in here we'll discuss tomorrow, because there are people very keen to get in, and also my time is up. Then tomorrow we'll continue from here.